Hello. Today we're going to study Archimedes' leverage law in a little more detail by introducing to you a new quantity called torque, or as they say in Spanish, torque. Sorry, that joke was a little dorque. First definition. Torque is a rotational force, or a force that causes rotation. Torque is specifically defined to be the perpendicular force times the distance away from a pivot point. You might recognize that F times a distance, which we called L before, but it typically is R, from Archimedes' law. Now, torque is represented by a Greek letter tau, which for all intents and purposes looks pretty much like a T, although a little italicized and maybe like half pi. And we typically use the letter R when using torques to represent the distance that force is away from the axis of rotation or the pivot point, and often that's called the radius. Now, torque has units. Its standard units are Newton meters. Unit of force is Newton. Unit of length is meters, or sometimes foot-pounds. It could have any units as long as it's force times distance, but typically we will convert things into newtons and meters. Now, for those of you who have a special appreciation for vectors, torque is technically an example of a cross product. It's the cross product of force and radius, and it has a direction which is given by the right-hand rule. So, typically, when considering torques, we discuss a concept called rotational equilibrium. That is, when all the torques are balanced on it, then it will either be not rotating, or it could be rotating at a constant speed. And that's when all the clockwise torques balance out all the counterclockwise torques. Typically, there are two different methods that can be used to solve these. The first is to set the sum of all the clockwise torques equal to the sum of all the counterclockwise torques. An alternative method is sometimes used, and that is you add up all the torques, assigning positive numbers to clockwise torques and negative numbers to counterclockwise torques. And if it's balanced, then the sum of all of those must be equal to 0. We'll typically use the clockwise equals counterclockwise because it's more intuitive. But when you're talking about unbalanced torques, then you might consider thinking about the net torque, like you consider the net force, and then the second option might make a little more sense. Now, most levers have some weight, and that weight must be accounted for. The weight of the object provides a torque that's acting as if it's a weight or a mass hanging from the center of the mass. So, as an example, we'll do two quick questions. One where we assume the bar has negligible weight, like we did in the first video. And second, when we consider what happens if the weight actually does matter. So, in this first example, I've got an object that's 1 meter away from the pivot point, opposite an object that's 5 meters away from the pivot point, and the equation that we'll use will say the counterclockwise torques, which in this case is this mass times its distance, has to equal the clockwise torques, which is the 10 newtons times its distance of 5 meters. And this is extremely simple to solve since it's just dividing by 1. That means x is exactly 50. And x is force, and so it would have a unit of newtons. Now, in this other example, we'll consider what happens if the bar has weight. Notice we drew in the weight of 10 newtons, and it is 2 meters away from the pivot point. That is because we need the 10 newtons to be located exactly halfway in the bar. If the bar is a total of 6 meters long, well, then that puts it 3 meters away from this end, or 3 meters away from this end, minus the 1 meter we have already got. That's where we come up with the 2. So, if we set up the equation like last time, the counterclockwise torques is just the weight, x, times its distance away from the pivot point. And on this side, I'll have two torques. I'll have this torque, which is 10 newtons times its distance away from the pivot point. And then I'll have this torque, which is coincidentally also 10 newtons, but it's now 5 meters away from the pivot point. So that gives us a total of 20 newton meters plus 50 newton meters, or 70 newton meters of torque equals x times 1 meter. Dividing both sides by 1 meter. So the meters cancel out, and we end up with 70 newtons this time. Now, when considering torques, the forces that are involved must be perpendicular to the lever. And if they are not, then we must find what component of the force is perpendicular. As an example, we've got 3 different diagrams. In this first diagram, there's 20 newtons acting down, and the 10 newtons on the end is acting not perpendicular, but actually parallel to the lever. The 10 newtons itself is actually contributing nothing to the rotation, and if we were to let this lever fall, the 20 newtons would win and push it, and it would fall down. Now, if there was some friction involved, I could see maybe an argument that it might be contributing something, but then the 10 newtons would be considered a normal force, and we'd have to figure out what the coefficient of friction is and all that to calculate how much of the force is perpendicular and contributes to the rotation. In the second diagram, the 10 newtons is actually doing some good to start balancing this. There is some component of the 10 newtons which is acting parallel. That's doing nothing. But then there is some component of the 10 newtons which is pushing upward, which is acting to counter the 20 newtons pushing down. So, in general, if you see down below, Fy is corresponds to that part which would be contributing to the rotation, and Fx, which is acting straight into the bar, parallel to the bar, would not contribute to the rotation. So here is an example, a pretty ugly example with a couple different forces and torques involved, and one that isn't drawn in at all. We're going to assume that the lever has a mass of 10 newtons again, and so one of the first things I'll do is try to figure out where is that 10 newtons located and draw it in appropriately. So the total length of the lever is 8.8 plus 4.2 meters, which is 13, and we assume that the 10 newtons is going to act as if it was all centered right at the center of mass, which would be, if we cut 13 in half, 6.5 meters away from either end. So 6.5 meters from this end. I've already gone 4.2 to get to the pivot point. Another 2.3 will get me to 6.5. So that would be approximately here. So I've got 10 newtons acting, and we said that is 2.3 meters away from the pivot point. So let's look at each of these torques and try to figure out what direction they would cause the lever to rotate. So this first force on the end is pushing down, which would cause the lever to rotate counterclockwise. This torque here is pushing up, which would act to push the lever clockwise. The weight of the bar is on the left-hand side, which would act to pull the lever back counterclockwise. And this torque on the end is pushing down, which would act to turn that side down or make a clockwise torque. So, in general, we have two forces that are acting counterclockwise, and two torques that are acting clockwise. The first counterclockwise torque is this force, and it is 8.8 meters away, So I'll write force times 8.8. And the other force that is acting counterclockwise is the weight of the bar, which is 10 newtons. And we said 2.3 meters away from the pivot point. Now the clockwise torques are both at angles, which means we're going to have to figure out what component of the 60 newtons is acting perpendicular. Now the shortcut is that when the angle is measured from parallel to the bar, as is usually the case, you would take the magnitude and multiply it by the sine of the angle. In general, I usually do 60 sine of 60 and 60 cosine of 60, and based on the drawing I can tell which number should be used. In this case, it seems that the torque perpendicular, or the force torque perpendicular, should be bigger than the force parallel. So if I do 60 sine of 60 and 60 cosine of 60, I should use the bigger of the two numbers. But this is a typical setup, so I'll just write 60 sine of 60. The first 60 is the newtons, and then sine of 60 degrees. So make sure that your calculator's in degree mode. The distance that this force is away from the pivot point is 3.2 meters. And then we'll add the torque on the end. That is, again, measured from parallel, so it'll be 16 sine of 70 degrees. And it's 4.2 meters away from the pivot point. And now we have an equation where the only variable we have is f here at the beginning, and so it's just a matter of time and we can calculate that. I multiplied a few of these out ahead of time. The 60 sine 60 and that times 32 or 3.2 works out to be 166.27 Newton meters. And then the 16 sine 70 times 4.2 works out to be 63.15 Newton meters. And so that gives us a total of clockwise torque of 229.42 Newton meters. On this side, I'll just rewrite it a little bit cleaner. 8.8 times F, and 10 times 2.3 is 23 Newton meters. If I subtract 23 from both sides, I get that 8.8 times the force has to equal 206.42 Newton meters. And dividing both sides by 8.8, we get that the force must be equal to 23.5 newtons. So now it's your turn. Here's a simple setup with one force acting up, one weight coming down, and let's assume again that the lever weighs 10 newtons, and that 10 newtons is located at its center of mass. Press pause and see if you can figure out how much weight could be hung.